Now that we have expressions for both the entropy and the internal energy of the lattice model, what we could do now is we could go out and calculate additional thermodynamic potentials, just using our typical strategies from before. So for example, if we want to get the Helmholtz energy of the lattice model, that's just going to be U minus ds. So we could plug in our U and our T minus S. So here's the T, and then the S term is this. So 1 minus rho ln of 1 minus rho. Okay? And then if we divide by n to get on a per molecule basis, we get this. Z. And notice now this is just a single row here. Okay, minus kBt divided by rho, and then p ln of, or rho ln of rho plus 1 minus rho ln of 1 minus rho. Okay, and so we're going to, this is our expression for the Helmholtz energy. Okay. In addition to the Helmholtz energy, we could also get the Gibbs energy, and more specifically, we get the molar Gibbs energy, which is just described by this. And so if we plug that in, we get this expression. kBt divided by rho ln of rho plus 1 minus rho ln of 1 minus rho. And then we have the pressure, and then since we had a V over N here, that's the same thing as saying divided by rho. Okay? And so now we have an expression also for the molar Gibbs energy. And remember, this is important because we know that at equilibrium, the molar Gibbs energy of the two different phases is equal to 0. Right? Or more specifically, to find when equilibrium occurs for a constant temperature and pressure, we know that equilibrium or coexistence would occur at the density value that minimizes that molar Gibbs energy. To visualize this, what we could do is we could think about this expression for G molar, and we could keep our temperature and pressure terms constant. And what we're going to do is we're going to vary rho. And so here, what we're seeing is a case in which we vary rho and what the molar Gibbs energy curve looks like. You remember, previously said for a one-component system, that's equal to the chemical potential. Okay. All right. So we see that at very low temperatures, right? So this is just saying some T1 less than some T2 value. Okay. We see that if we plot G molar versus rho, that the curve, basically has one sort of minimum here, right? And so at that one minimum, we essentially just have a single phase that occurs. As we increase temperature, we see that this inflection point that we saw here starts to become get lower and lower, right? But at T2 is less than T3, this rho value still gives a lower overall free energy than the minimum here. So we still have one phase. But when the temperature is equal to the boiling point temperature of the system, we now see that the Gibbs energy here is equal to the Gibbs energy here. So the two minima have the same value. It's at that point where now the system is capable of phase separating into a low density phase, so a vapor, and a high density phase, a liquid in this case. And then if you keep going to higher temperatures, then this minimum is lower than this one. And so we're always just going to be in that low density phase, or in other words, the vapor. And so just to indicate, this is the vapor phase, and then this is the liquid phase. Right? And so that's another way to visualize the phase transition using your molar Gibbs energy plot. Okay? And so here we're varying our density parameter. And so in the context of thermodynamics and physics, we would describe how we're using density in this case. We would say that our density serves as an order parameter. Right? And so an order parameter is just a term that is used in physics to describe an internal degree of freedom that governs the phase behavior of the system. Okay? All right, and so for other sorts of systems, you could use density, or you could use mole fractions or volume fractions. It just depends on what the more easily measured sort of property is. Okay, and so one thing I'll also mention is if you want to find the boiling point temperature and vapor pressure from the lattice model, since we now have expressions for the Gibbs energy and things like that, you could just use the same strategies that we used before. Right, so okay. All right, one other thing I want to point out, we have an equation for G molar, and we know by definition that's just H minus Ts. And if we take a look at this equation here, based on how these terms are set up, we could say that the enthalpy term in the lattice model is this. While the entropy term is this. Okay?